Let's learn about global wind patterns. So, if you'll recall from our previous lesson, convection is the upward movement of hot fluids, liquids or gases, in the case of the atmosphere, gases, and the downward movement of cooled gases. And it's a result of uneven heating, in this case, of the Earth's surface. So, in areas where the Earth's surface is hot, the hot ground makes the air warm. Warm air becomes less dense and floats upwards, cools off and sinks back down, creating these circular patterns we call a convection cell. Now, a convection cell can happen, as seen in this image here, at a small scale. It could be as small as a air rising off a parking lot. But they could also happen, it was proposed in the 1800s by a gentleman named Hadley, at a global level. It could happen, look, it's hotter at the equator, it's colder at the poles. Should we get a convection cell? So this gentleman named Hadley suggested this. He said, look, air should rise at the equator because the sun's rays are more intense here, they're more concentrated, and it should sink at the poles because the air here is going to be cold because the sun's rays are more spread out and deliver less energy. So what Hadley proposes, we should see a global level convection pattern in which air rises at the equator, sinks at the poles, and at the surface of the Earth, it should flow in a direction that carries it from the poles to the equators. All right, and this is what we would have, except for two things. One is there are continents, which breaks up this pattern, and the other one is, and more important, is that the world is spinning, and because the world is spinning, this flow is going to be deflected a bit in different directions. So let's try to learn this. It can be a little bit tricky at points, but let's hopefully get you through that. So let's start off with this. Instead of having one big convection cell in each hemisphere that goes from the pole all the way to the equator and back, it gets broken into three, basically at 1/3. So this is 0 degrees, this is 90 degrees. So at 30 degrees and 60 degrees, we have breaks. So a third of the way. So so basically, instead of, and this happens in both hemispheres. So instead of just having one large hemispherical convection cell, I get three of them, and they have names: the polar cell, the Faro cell, the Hadley cell. Let's take a closer look at the ones in the northern hemisphere. They're the same in the southern hemisphere. It's just they go in the reverse order. So the cell that is closest to the equator is the Hadley cell. In the Hadley cell, which is definitely the most pronounced of them, the one that has the most aggressive motions, intense heating at the equator causes air to rise at the equator, and then it sinks at 30 degrees. So it flows along the surface of the world from 30 degrees towards the equator. So at the surface, the air is moving towards the equator. It's a little bit harder to understand the Faro cell, so let's just jump up here and talk about the polar cell. It makes sense that air should sink at the pole because it's cold there. Cold air sinks, so I have air dropping down here. It doesn't make as much sense that it should rise at 60 degrees, but it has to rise somewhere. And remember, it only makes it a third of the way. So it rises at 60 degrees, and then it sinks back here. So I have this one here, this polar cell. And again, if you notice, the air at the surface is flowing from the poles towards the equator. Now, the Faro cell is caught in between these two. So if you can remember that air is going to rise at the equator and therefore sink at 30 degrees, it's going to sink at the pole and rise at 60 degrees. If you can draw these two, then you can remember this one. This one is basically sympathetic to the other two. Air is sinking here, so the air in the Faro cell sinks at 30. Air rises in the polar cell at 60, so air in the Faro cell rises at 60. So I have this one in between these two. Well, let's zero in on the Hadley cell. As I said, because the sun's rays are so intense here, it's a very powerful convection cell. The winds are very strong and consistent, more so here than in the other cells. Now, a couple things to consider. One is that as air at the equator rises, remember, anytime air rises, the pressure is going to be low because you're moving atoms from the area. So we associate low pressure with equatorial regions. As this air rises, then it's going to cool off, and the water vapor is going to condense and precipitate out. So we'd expect to have lots of rain at the equator. And in fact, we do. The equator is literally ringed with rainforests. It rains a lot at the equator all the time because of this Hadley cell convection. But now consider this. As this air goes up, it loses its moisture at the equator. So this air up here in the Hadley cell is dry air. So this air that's traveling near the top of the troposphere, this is very dry air, and it comes back down around 30 degrees. And when it comes down, it's going to make high pressure, because remember, when you add air to an area, the pressure goes up. So near 30 degrees, I would expect to find high pressure and dry air because the air lost its moisture on its way up. So as a consequence, just as I find rainforests along the equator, I tend to find deserts near 30 degrees where this air sinks down. And that's true in both the northern hemisphere and the southern hemisphere. Let's take a look at the actual planet to see what I'm talking about here. So here's a Google Earth image of Africa. We see the equator here, and along the equator, lo and behold, we have rainforests. Most of Africa is not forested, but it is at the equator because of this Hadley convection. At 30 degrees, where the air rises now, it sinks at 30 degrees. Notice at 30 degrees, it's an arid region. And it rises here and it sinks at 30. At 30 degrees, again, we have this arid region. So it's not that you can't have deserts in other locations. It's just that at 30 degrees, you have descending air, and that descending air tends to be dry. Just remember, falling air tends to be dry because it loses moisture on the way up. Please get that idea into your head because it's an important one. Now, at the surface, the general motion of air in the Hadley cell is from 30 degrees towards the equator. Whether we're in the northern hemisphere or the southern hemisphere, the air is trying to move from 30 degrees towards the equator. If the world didn't spin, that's exactly what it would do. But the world does spin. And because of the spin of the world, instead of seeing this pattern, we see this pattern. It's deflected westward. All right. Now, I would recommend you simply memorize the fact that air that is moving towards the equator will deflect to the west. You should just memorize that one because it's easy to get confused when you try to reason it through. But I'm going to try to get you to understand why. It's a thing called the Coriolis Effect. And so let's just see if I can get you to understand. So the idea is what we find is air is moving in a generally westward direction between 30 degrees and the equator. It's moving in a generally eastward direction between 30 degrees and 60 degrees. And it's, again, moving in a generally westward direction when I get between the poles and 60 degrees. So we have these global wind patterns that are established that are a consequence of these three convection cells, the Hadley, the Ferrel, the polar, and the fact that winds moving either towards the equator or away from the equator get deflected by the spin of the Earth. That's what gives us this general direction of the winds. That's why they're not just south to north or north to south, but they have a tendency to move east to west or west to east as well. Why? Okay, it's called the Coriolis effect. I'm sure you've heard of the Coriolis effect. I'd be surprised if you really had a good grasp of it. Most people at your age most people in the world don't have a good grasp of it. What am I talking about? So here's the way to think of it. If you stood at the North Pole, in the course of one day, you would go nowhere. You would just turn around like a record on a record player. You wouldn't, of course, you probably don't know what that is, but you wouldn't go anywhere is the point, okay? But if you walk away from the pole, so now what happens is now if you're standing here in the course of one day, you'd go, you'd be traveling, let's just say, 500 miles an hour, right? Because in the course of a day, you're traveling somewhere. And the farther you get away from the pole, the greater distance you're going to go in the course of a day. So the greater your velocity until you get to the equator and you reach that maximum speed. You have the maximum radius. And so at the equator, you're literally traveling 1,000 miles an hour or 650 kilometers an hour. You're traveling fast. So the point is, the matter at the equator is traveling very fast, and matter at the pole is not moving at all. So as you move from the equator towards the poles, you're slowing down. If you move from the poles to the equator, you're speeding up. And this causes a deflection of moving air masses. Let's see why. And I hope this works for you. It may not, but let's just try this. So imagine if we were in two cars, and these two cars are moving at the exact same speed, 40 kilometers an hour. And the person in car A is going to throw an object to the person in car B, and let's just pretend that there's no friction. So there's nothing that's going to physically cause these things to move, slow down. Okay, right? So what happens is person A throws it. Well, a moment later, when it's halfway in between, since car A and car B and this object are all traveling this way at the same speed, it's still right in between car A and car B. And in fact, when it reaches car B, it's still right in between the two. So a person in either car observing the motion of this object would say it went in a straight line. They would see it do this. Okay. Now, and what's tricky about Coriolis effect is you have to shift what's called your reference frame, and that's hard for us to do. It tends to confuse us. But the idea is, if you were in that car, you would see that object just going in a straight line between the two cars. But what if the cars are not going the same speed? What if car B was going faster? What if car B was going faster than car A? So when car B is going faster, but when it gets right next to car A, they're side by side, the person in car A does the exact same thing, throws it exactly the same way. But what happens is when this object gets halfway between the two, it's still going the same speed as A in this direction. So it's still even with A. But since B is going faster, it's now behind B. In fact, by the time it gets to where B was supposed to be, it's considerably behind it. See, I got to drag myself down here. There you go. It's considerably behind it. So basically, when the object, whether it be a ball or an air mass, is moving from a slow area to a fast area, look how it deflects. It would appear to have deflected this way, even though it moved in a straight line, but it had this apparent movement in a particular direction. It got moved in this case to the left. It got moved, so it came in behind the faster object. Now, what does that have to do with wind patterns on Earth? Well, okay, wait, we're going to try this first too, and then we're going to take it all at once. So let's just say instead the person in car B threw the ball to car A. This ball is moving 80 kilometers an hour, same as person B is, but car A is only going 40. So a moment after throwing it, the ball is still even with car B because it's traveling 80 kilometers an hour this way as it moves that way. So it stays up with car B, but car A is falling behind now. In other words, the ball is ahead of car A, where it wasn't before. And by the time it gets to where car A is supposed to be, the ball is considerably in front of car A. So what would these people see? Well, they would see a deflection like this in the other direction. So they would see it coming in ahead of the slower. Now, if we look at the planet Earth, here's what we notice. If the world didn't spin, air moving in the Hadley cell from 30 degrees to the equator would move straight down. But this is going faster than this. If you're at the equator, you're traveling faster. So as this comes towards you, you're going to move this way and it's going to come in behind you. So we see this pattern of deflection. Air moving this way comes in behind you, right? Because if you were here when the air started moving, you're here now, so it comes in behind you. So we get this general deflection this way. Now, that's why we get these directional flows of air at Earth's surface, is because of a combination of the convection makes it want to move, in the case of the Hadley cell, from the latitude 30 to the equator, and then because it's moving slower at the starting point than it is at the finish point, it deflects this way. Now, if you just look, whether I'm in the northern hemisphere or the southern hemisphere, it's always going to be deflected in a way where it comes in basically behind the equator. So what that means is, if you notice, in both cases, it's deflecting to the west. If this is the North Pole, this is the west. In both cases, it deflects westward. So you can simply memorize that, or you could try to picture what's happening in terms of Coriolis effect. So in the Hadley cell, where air is rising at the equator and then sinking at 30 degrees and returning from 30 degrees to the equator, so it's moving moving towards the equator at the surface, it deflects in a westward direction. So we get what we call the trade winds. So between 0 degrees and 30 degrees, we find winds that tend to blow in this direction. And the closer I get to the equator, the more westwardly they go. So we have these winds, and they're called the trade winds because what would happen is sailors used to, before there was coal-powered ships, they would have to use sail power. They would sail, if they wanted to get from Europe to the Americas, what they do is they would sail southwards, catch these winds, and these winds would blow them across the ocean. So they called them the trade winds. They were the way to get where you were going. You get these trade winds, and you are going to travel westward pretty quickly. But the thing is, you can only travel westward. That no matter where you are in the world, if you're between 30 degrees and the equator, these winds are going to blow you in a generally westward direction. Now, so we call them the trade winds. If the ones here are called the northeast, the ones here are called the southeast. The east thing, I get why it would bother you. I'll talk about it in a minute when I talk about the Ferrel cell. So now, in the Ferrel cell, here I have air just trying to move away from the equator. Now, this air is moving faster than this air. So when this air gets here, it comes in ahead of where it was basically thrown from. So it's just like the ball coming in ahead of the other car instead of behind it. And so we get this general bending in an eastward direction, whether I'm in the northern hemisphere or the southern hemisphere. this combination of air moving away from the equator and being deflected by the spin of the Earth always causes it to have a general eastward movement to it. Now, unfortunately for all of us, sailors name winds for the direction they come from. So if I talk about the north wind, it means I'm looking at the north and it's blowing in my face. The north wind comes out of the north. So what they call these winds here are the prevailing westerlies. They're deflecting to the east. If I let a balloon go, the balloon will move across the ocean in an easterly direction. But we call them the westerly winds because they seem to be coming out of the west. If I was facing the wind, I'd be facing west. So between 30 degrees and 60 degrees, as the air in the Ferrel cell is trying to move away from the equator, it deflects eastward, and it provides us with winds we call the prevailing westerlies. So here's what people used to do. If this was Europe, because it's the Pacific Ocean, let's just say it was Europe, they would leave Europe, they would sail south along the coast until they got into the trade winds, which are between 30 degrees and the equator, and that would blow them across the Atlantic Ocean. Then what they'd do is they'd make their way up here until they could get to the westerlies, and that would blow them back across the ocean to Europe. So that is how people navigated in the days of wind power. So I already talked about the trade winds. I already talked about the prevailing westerlies. Okay, and then there's also what we call the polar easterlies. So at the poles, and these are less important because, I mean, I guess they're important if you live in Canada, but they follow the same directional pattern as the trade winds, because here the air is trying to move towards the equator, so it's going to bend to the west. Oh, I put a slide there about the polar easterlies. Okay, now the boundary regions between these are interesting because they tend to be regions where there isn't a lot of wind. And so these were named by the sailors who would get stranded because they were relying on wind power. So as sailors tried to cross between the northern hemisphere and the southern hemisphere, they'd get to the equator itself, and they would run out of wind. There's no prevailing wind direction at the equator. They call it the doldrums. It might take you a week to get from here to here. It might take you 3 weeks to get from here to here because there's just no wind to move you. There's no prevailing direction of wind motion. And the same thing is true between the Hadley cell and the Ferrel cell. So we have this region here that they call the horse latitudes, where again, there just wasn't much in the way of air movement. And then there's also one called the polar front at the boundary between the polar cell and the Ferrel cell. Now, I doubt if this next part is going to be on the test, but I just think it's interesting, so I'm going to throw it in here anyway. You probably have heard of jet streams. Jet streams were discovered by American bomber pilots at the end of World War II, when they first invented high-flying bombers that could get up high. They could fly in the stratosphere, and they could avoid being attacked by Japanese fighters because they were too high for them to get to. But what they found is they were very ineffective because when they dropped their bombs, the bombs they dropped always end up far, far, far to the east of their targets. And so meteorologists realized, oh, well, we didn't figure this, but there's this rivers of air in the upper part of the troposphere near the tropopause, and they call them the jet streams. And there's one of them between each of the cell boundaries. So basically, the strongest one is what's called the polar jet. It's between the Ferrel cell and the tropopause. And there's another one, the subtropical jet, which is found closer to 30 degrees, which is found between the Hadley cell and the Ferrel cell. Now, for reasons that I don't quite understand, and I've tried to find a good explanation for them, and I can't find it, the air in these has a general eastwardly flow to it, and it can be quite fast. So air in these things is just howling in the generally eastward direction. I say generally because it has a little bit of a sinusoidal pattern to it, like a snake. And this isn't it's not like it's always here. Sometimes this will move up this way and this will move down this way, but the air is always traveling from west to east quite fast. We're talking like up to 400 kilometers an hour. And the reason this is worth noting is, and the speed changes depending on how cold the air is on one side, how warm it is on the other side. And as this thing undulates, it can push air masses from one side to the other. Now, one thing that's interesting is the airlines take advantage of this. So if they're traveling eastward, they will fly up into it, and it will carry them eastwardly. It's basically like jumping into a river that carries you in the direction you want to go. And so if you travel eastward, like say you leave Seoul and travel to America, chances are it'll take a lot less time to get to America than it takes to get from America back to Seoul, because when you leave America, Now you're going the opposite direction. So what they'll do is they'll avoid the jet stream, but they won't have that assist of being carried along by that river of air. And it's worth noting that these things are constantly shifting, and as they shift, like as this one moves downwards, whatever weather system is here will get pushed in a southerly way. And as this one here starts to move upwards, it'll take this air and move it that way. So these jet streams have a tendency to form what are called troughs and ridges that then push weather systems around. So a lot of the weather in the northern hemisphere, the northern and southern hemisphere, is put in motion by the undulations of these jet streams. And then here's some videos you can watch on. So I'm sorry this one was kind of long. Thanks for watching. And hopefully you'll be able to complete your activity and understand what you're doing.